You're settled into your seat, seatbelt fastened, the cabin lights dimmed, and the engines spool up with that familiar rising whine. You've done this 100 times. You know the routine. Taxi, takeoff, climb, cruise. But here's what nobody tells you. Just inches from your elbow, behind that window shade and inside the fuselage wall, a network of systems is running diagnostics that would make a NASA control room jealous. And the most fascinating part, you've been interacting with these systems your entire flying life without ever knowing they exist. That little button you press to dim the window, it didn't control a shade. There's no shade in that window at all. The darkening effect is created by a liquid crystal layer sandwiched between two sheets of glass. And when you press that button, you're sending a command through a data bus that shares wiring with the flight control computers. Boeing's 787 Dreamliner uses a 115-volt electrical charge to align those crystals and let light through. Turn the charge off. The crystals scatter randomly and the window goes dark. The delay you sometimes notice, that half-second pause between pressing the button and seeing the window change, is the time it takes for the charge to dissipate. You've been operating an electro-optical system every time you wanted to block out the sunrise over the Atlantic. But the window is just the beginning. The real story is what's hiding behind every panel, every vent, every button in this cabin. Systems engineered with a level of redundancy that borders on paranoia, designed to keep you safe through scenarios that sound like fiction. And by the time we're done, you'll never board a plane the same way again. You'll see the invisible architecture holding the entire experience together. There are two things I need you to keep in your mind as we go deeper. First, the black paint on the nose of the aircraft. You've seen it on every flight, that dark rounded cone at the very front. Most passengers assume it's aesthetic or maybe some kind of de-icing surface. But the truth is far more surprising. And second, the quiet hum you hear during taxi while the engines are idling. That low vibration that seems to come from everywhere and nowhere at once. Those two details are connected in a way that reveals the genius of what you're about to discover. So here's the promise. By the end of this video, you'll understand exactly what that black nose cone is hiding, why that hum is the sound of survival, and how a system designed in 1939 is still protecting you at 37,000 feet today. Let's start with the thing you see every time you walk to your seat but have probably never really looked at. Have you ever noticed that the nose of most commercial jets is painted black? It's not a design choice. It's not a branding decision. It's not even paint in the traditional sense. That black surface is a radome, a combination of radar and dome. And it's one of the most critical components on the entire aircraft. Behind that rounded shell, spinning at about 25 revolutions per minute, is a weather radar antenna that scans the sky ahead for thunderstorms, wind shear, and turbulence. The radar beam itself is powerful enough that the nose cone has to be transparent to radio waves, which is why it's made of glass fiber composite instead of aluminum. Paint would block the signal, so the radome is left exposed in its natural dark gray color, which happens to look black against the sky. But here's where it gets really interesting. That radome isn't just a protective shell. It's an aerodynamic surface engineered to precise tolerances. Any deviation in its shape, even a dent smaller than a coin, can distort the radar beam and send false weather readings to the cockpit. During a lightning strike, the radome's static discharge wicks carry the electrical current safely around the antenna and into the fuselage skin, protecting the sensitive electronics inside. Boeing's maintenance manuals specify that radome surface roughness cannot exceed 32 microinches, and any repair must be tested for radio frequency transparency before the aircraft returns to service. Now, think about what this means for a moment. Every time you board a plane and walk past that black nose, you're passing a piece of engineering that has to be simultaneously strong enough to withstand bird strikes at 200 knots, transparent enough to let radar waves pass through, and aerodynamic enough to maintain laminar airflow over the entire forward fuselage. And it's been doing this job since the 1940s, when the first weather radars were installed on commercial aircraft. But the radome is also hiding something else. Behind it, mounted directly to the forward pressure bulkhead, is the air data computer. This is the brain that calculates your airspeed, your altitude, your rate of climb, and dozens of other parameters that the pilots rely on every second of the flight. The air data computer receives input from pitot tubes and static ports mounted on the outside of the fuselage. Those small metal probes you can see if you look carefully near the nose. And here's the key detail. The air data computer is triple redundant. There are 3 independent computers, each receiving data from 3 independent sets of pitot tubes, and they vote on the correct values 3 times per second. If one computer disagrees with the other 2, it's automatically overridden. You've probably never thought about those pitot tubes, but they're the same system that failed on Air France Flight 447 in 2009. Ice crystals blocked the pitot tubes. The air data computers got confused and the autopilot disconnected, leaving the crew to handle a situation they weren't trained for. That tragedy led to a complete redesign of pitot heating systems across the industry. Now those tubes are heated to over 200 degrees Celsius, even on the ground, to prevent ice from forming during flight. The system that failed that day has been replaced with technology that has never failed since. So when you look at that black nose cone, you're not just seeing a radar cover. You're seeing the physical interface between the aircraft and its most critical sensor network. The system that tells the computers what the atmosphere is doing. And the computers are listening. But here's the part that most passengers never think about. That radome and its radar antenna are connected to something even more fundamental. Something that lives deeper inside the aircraft structure and has its own story of survival. Remember that hum I mentioned during taxi? The low vibration you can feel through the seat and the floor? Most people assume it's the engines idling, and they're partially right. But the sound you're actually hearing isn't the engines themselves. It's the bleed air system. Every commercial jet engine is essentially a giant air compressor. A fan at the front pulls in massive amounts of air, and a core section compresses that air to high pressure before mixing it with fuel and burning it. But not all that compressed air goes to the combustion chamber. Some of it is bled off, siphoned away through valves in the engine casing, and routed throughout the aircraft. This bleed air is the lifeblood of the entire plane. It's used to pressurize the cabin, to heat the wings and prevent ice from forming, to start the engines on the ground, and to power the air conditioning packs that keep you comfortable. The temperature of bleed air leaving the engine can exceed 400 degrees Celsius, so it has to be cooled through a series of heat exchangers before it reaches the cabin. The system that manages this is called the pneumatic system, and it's controlled by a computer called the bleed air management controller. But here's where the disruption happens. You've been conditioned to believe that the cabin pressurization system is simple. That the plane just pumps air in and lets air out through some kind of valve. The reality is far more complex. The outflow valve, which releases excess cabin pressure to maintain the correct altitude inside the aircraft, is controlled by a digital computer that adjusts its position based on no fewer than 12 different parameters. It reads the cabin pressure, the outside pressure, the rate of climb, the engine thrust setting, the bleed air valve positions, and even the position of the landing gear. If the landing gear is down, the outflow valve is programmed to move to a specific position to prevent pressure surges during landing. And all of this happens without any pilot input. The computers manage the entire pneumatic system automatically, adjusting bleed airflow rates, cooling temperatures, and cabin pressure levels faster than any human could. The pilots have a simple cabin altitude gauge that tells them what's happening. But the system is designed to be completely self-managing. If you're comfortable at cruise altitude, it's because a network of valves, sensors, and computers has been working silently since the moment you left the gate. But this is where the hidden paradox comes in. The same bleed air system that keeps you alive is also the most common source of mechanical failures on commercial aircraft. The valves that regulate bleed airflow are subjected to extreme temperatures and pressures, and they fail more often than almost any other component on the engine. When a bleed air valve fails, the cockpit gets a caution message, and the crew has to follow specific procedures to shut down the affected system and reroute bleed air from another engine. On a twin-engine aircraft like the 737 or A320, each engine provides bleed air to its own side of the aircraft, with a cross-feed valve that can connect the two sides if one fails. The entire system is designed so that a single failure never leaves the aircraft without pressurization. Now here's the self-recognition moment. You felt the cabin pressurization change during descent. That slight pressure in your ears that makes you yawn or swallow. That's the outflow valve opening wider to release cabin pressure at a controlled rate, matching the aircraft's descent profile. The computer is managing that pressure change so smoothly that you barely notice it. But if you've ever flown on a plane where your ears popped suddenly and painfully, you've experienced a moment when the outflow valve was adjusting more aggressively than normal. Perhaps because the aircraft was descending faster than usual, or because the pressurization computer was compensating for a different bleed air configuration. The system that's managing your comfort at 30,000 feet is the same system that has to handle the most extreme conditions imaginable. And the engineers who designed it built in a fail-safe that very few people know about. But before we get to that, I need to show you how the bleed air system connects to something you've probably never considered. The hydraulic system that powers the flight controls. Bleed air doesn't just pressurize the cabin and heat the wings. It also drives a critical backup system that keeps the plane flyable when everything else fails. On a Boeing 777 or Airbus A330, hidden inside the left-wing fuel tank, there's a device called the air-driven demand pump. It's a hydraulic pump powered entirely by bleed air from the engine. No electricity required, no mechanical connection to the engine shaft. Just compressed air spinning a turbine that drives a hydraulic pump. This pump exists for one reason. If the main engine-driven hydraulic pump fails, the demand pump can maintain hydraulic pressure for the flight controls, landing gear, and brakes. Think about what that means. The hydraulic system that moves the ailerons, the elevators, the rudder, the flaps, the slats, the spoilers, and the landing gear. All of it can be powered by a pump that's driven by nothing more than hot air from the engine compressor. And this isn't a theoretical backup. Airbus documentation states that the air-driven demand pump can sustain full flight control pressure for over 40 minutes with zero assistance from the main hydraulic system. 40 minutes is enough to descend from cruise altitude, divert to an alternate airport, and complete an approach and landing. But the engineers didn't stop there. They added a second backup system that doesn't rely on bleed air at all. Enter the ram air turbine, the RAT. If both engines fail and both hydraulic systems go dark, a hatch opens in the belly of the aircraft and a small propeller drops into the airstream. The airstream spins the propeller, which drives a hydraulic pump and an electrical generator. The RAT can provide enough hydraulic pressure to operate the flight controls and enough electrical power to run the essential instruments and radios. A 2018 NTSB incident report documents a British Airways flight that relied solely on the RAT for landing gear extension and braking after a dual-engine failure over the Atlantic. The RAT deployed automatically, the crew flew the approach by hand, and the aircraft landed safely with no injuries. Now, here's the escalation that ties everything together. The RAT isn't just a modern invention. The first ram air turbine was installed on a commercial aircraft in 1939, the Lockheed Model 10 Electra. That aircraft flew with a RAT that provided emergency hydraulic power to the landing gear and flaps. The design hasn't changed in its fundamental principle in over 80 years. A small turbine spinning in the wind, generating power from nothing but the aircraft's forward motion. It's one of the simplest and most reliable backup systems ever designed. And here's the part that changes everything. The RAT is connected to the same hydraulic system that powers the flight controls you've seen move before takeoff. When the pilots do their control checks on the ground, moving the yoke and watching the ailerons and elevators respond, they're testing the main hydraulic system. But if the RAT had to take over, it would pressurize the exact same actuators through the exact same hydraulic lines. The system is designed so that every flight control surface can be powered by any of the three independent hydraulic sources: the engine-driven pumps, the air-driven demand pump, or the RAT-E. This level of redundancy isn't accidental. It's the result of decades of accident investigation and engineering refinement. After the 1979 American Airlines Flight 191 crash in Chicago, where an engine separation severed hydraulic lines and caused a loss of control, the FAA mandated that all new aircraft designs must have hydraulic systems segregated so that no single failure can disable more than one system. The Airbus A320, introduced in 1988, was the first commercial aircraft to fully comply with this requirement. With three independent hydraulic systems running through physically separate parts of the fuselage. The next time you feel that hum during taxi, you're not hearing the engines. You're hearing the bleed air system pressurizing the hydraulic reservoirs, charging the demand pump, and preparing the aircraft for flight. And you're also hearing the first layer of a defense chain that includes a backup pump in the fuel tank and a wind turbine in the belly. Three independent systems, each capable of keeping you safe, all designed before your flight even began. But there's still one more piece to this puzzle. A piece that involves the black nose cone and the bleed air hum in a way you've never considered. That black nose cone and that bleed air hum are connected by something that sits right at the intersection of both systems. Behind the radome, mounted directly to the forward pressure bulkhead, there's a component called the bleed air precooler. It's a heat exchanger that takes bleed air from the engine, air hot enough to melt aluminum, and cools it down to a safe temperature before it enters the pneumatic distribution system. But here's what most people don't realize: that precooler uses outside air from the radome area to do its cooling. Ram air scoops built into the forward fuselage just behind the black nose cone funnel outside air directly into the pre-cooler at over 200 knots during cruise. The pre-cooler then dumps that heated ram air overboard through a vent that you've seen 1,000 times. That small rectangular opening just behind the radome on the lower fuselage. So the next time you look at that black nose cone, you're not just looking at a radar cover. You're looking at the air intake for the system that makes bleed air survivable. Without that pre-cooler, the pneumatic system would deliver air to the cabin at temperatures that would melt the ductwork. The entire temperature regulation of the aircraft depends on that small heat exchanger sitting behind the radome, cooled by air that enters through a scoop you've probably never noticed. But the pre-cooler is only part of the story. The bleed air system also feeds the cabin pressurization controllers. There are two of them, one active, one standby, and they're mounted on the forward electronics bay, which sits directly behind the radome. These controllers receive input from the air data computers I mentioned earlier, and they use that information to position the outflow valve with precision that's measured in degrees of rotation. The outflow valve doesn't just open and close like a door. It modulates its position continuously, opening slightly when the aircraft climbs and closing when it descends, maintaining a cabin altitude that never exceeds 8,000 feet, even when the aircraft is cruising at 37,000. And here's the detail that ties everything together with that hum you feel during taxi. During the pre-flight checks, the bleed air management controller runs a full diagnostic on every valve in the pneumatic system. It opens and closes each valve in sequence, monitoring pressure sensors to verify that the valves are responding correctly. The low hum you feel is those valves cycling, opening, closing, testing themselves, while you're still sitting at the gate. The aircraft is performing a self-diagnostic on the system that will keep you alive at altitude, and you can feel it through the seat of your pants. Most passengers write it off as engine vibration. Now you know better. But what about the scenario where the bleed air system itself fails? If a bleed air valve malfunctions and cannot be closed, the crew has a procedure called engine bleed off. They pull the bleed air switch to the off position, which closes the isolation valve and stops all bleed air from flowing from that engine. The aircraft can operate on a single bleed source, with the cross-feed valve open to supply both sides of the pneumatic system. And if the remaining engine's bleed air system also fails, that's when the backup compressors come into play. On some aircraft, there's an electric-driven compressor that can supply bleed air if both engines are unavailable. It draws power from the auxiliary power unit, the APU, and provides enough pneumatic pressure to keep the cabin pressurized and the air conditioning running. The APU, sitting in the tail cone of the aircraft, is essentially a small jet engine in its own right. It runs on the same jet fuel as the main engines, and it's designed to start within 60 seconds at any altitude up to 30,000 feet. The APU can provide bleed air for engine starting, cabin pressurization, and air conditioning, all while the main engines are shut down. It's the ultimate backup to the backup, and it fires up automatically in certain failure scenarios without any pilot command. So when you look at that black nose cone and feel that bleed air hum, you're witnessing a cascade of redundancy that spans the entire aircraft. The radome protects the weather radar that tells the pilots where the storms are. The air data computers use pitot tubes to measure the atmosphere. The bleed air system pressurizes the cabin and powers the demand pump. The demand pump backs up the main hydraulics. The rat backs up the demand pump. The APU backs up the engines for bleed air, and every single component is monitored by a computer that will alert the crew at the first sign of deviation. Now, I want you to think back to the last time you were sitting in your seat waiting for takeoff and you heard that low hum. You now know what it is. You now know why it matters. And you now know exactly how many layers of engineering are standing between you and a system failure. But there's one more thing that connects all of this. One final piece of engineering that brings the entire story full circle. It involves that same black radome and something you've never seen because it's hidden inside the cockpit instrument panel, the primary flight display. The screen that shows the pilot's artificial horizon receives its attitude data from a device called the inertial reference system. And that inertial reference system has a secret that traces back directly to the same design philosophy that created the radome and the bleed air system. The IRS, as it's called, doesn't use external sensors or radio signals to determine where the aircraft is pointing. It uses 3 laser gyroscopes and 3 accelerometers, all mounted inside a sealed block of aluminum that weighs precisely 11.5 pounds. The lasers in these gyroscopes travel in opposite directions through fiber optic coils, and the difference in their arrival times reveals the aircraft's rotation with an accuracy of 1/10,000th of a degree per hour. That precision is what allows the pilots to fly through zero visibility conditions and still know exactly where the yaw ground is. And it's protected by a housing that was originally designed for a completely different purpose: to survive the extreme shock and vibration of being mounted inside the radome area of military aircraft. The same engineers who designed the bird strike resistance of the radome also designed the mounting system for the inertial reference units. The connection isn't accidental. It's the result of a design culture that treats every component as a potential failure point and engineers it accordingly. Script sanitized, removed 27 chars, LLM preamble leak.
Let's double check the connection points on the physical valve itself.